Okay, guys, this video is on ANOVA. It's analysis of variance. And ANOVA is a procedure developed by Fisher back, I don't know, kind of, let me check my history here. Probably right after World War I. So I'm saying probably 1918, 1919, somewhere in there. Fisher is, without question, one of the most prominent statisticians. I think if anyone's compiling a list of famous statisticians, certainly Fisher and Tukey and Friedman and Pearson are going to be on that list. Most people, Fisher would probably be at the top. So now that you know far more about prominent statisticians than you ever cared to know, let's go ahead and make this happen, okay? Okay, guys, ANOVA reminds, a good way of thinking about ANOVA is it's very similar to a pooled t-test. Similar, but not the same. Sort of, but not really, right? What we start out with in a pooled t-test is we start out with population number 1 and population number 2. So a pooled t-test, a two-sample t-test, deals with two populations. We make the assumption that the population variances are equal. And when we have that condition, it is very safe and appropriate to use a pooled two-sample t-test. The null hypothesis would be that H sub O, well, our null hypothesis would be that mu1 equal to mu2, which is the same thing as testing that the difference in the means, mu1 minus mu2, is equal to 0. Now, what happens with ANOVA? Well, ANOVA comes in and we have at least a third population. And very, very likely even more. And what I like to say, the notation that I use, we have K population. So each of these populations has, its own variance. Okay. Now, moving this into ANOVA, we now make the assumption. Okay, let's get rid of this right here. That all of the population variances are equal. And in which case, the null hypothesis is that all of the population means are the same, they're equal. And the alternative hypothesis is at least one pair of means is different. So again, extending the two-sample pooled t-test into ANOVA is just the technique of comparing the equality of means from essentially more than two groups. Now, what was done before Tukey came up with ANOVA is people would do multiple t-tests. And this turns out this is bad. This is not good. Okay, multiple t-tests lead into what's called a inflation of the family-wise type 1 error rate. Now, if you think about it, if we would have 4 groups, when we do multiple comparisons, when we just compare 1 and 2, we have a 5% chance of committing a type 1 error. If we compare 1 and 3, well, we have a 5% chance of committing a type 1 error there. Compare these, compare these, compare these. Look at all the possible pairwise comparisons. Every time you have an alpha of 0.05, you can show that the new alpha value can be approximated by taking 1 minus 0.95 raised to the k power. So you can quickly put this in your calculator and see if you have 4 groups. I think it turns out to be create an alpha of about 0.18. So the likelihood, probability of you committing a type 1 error if you conducted multiple t-tests would be increase 3.5, almost 4 times. Well, in statistics, we can't have that. We can't have the possibility of committing a type 1 error that heavily inflated. So to control for this, the family-wise type 1 error rate being inflated, Fisher came up with ANOVA. Now, ANOVA has certain assumptions that have to be met, and there are 3 assumptions for ANOVA. The first assumption is normality. Each of our populations should be normally distributed. The next assumption has to be satisfied is the homogeneity of variance assumption. That's just a fancy schmancy way of saying we need equal variances. Pretend that's a K. And pretend that's a 2. And the last thing we need is we need independence. Independence is by far the biggest threat to the stability of our p-values. Studies show that slight variation in normality, p-values are still pretty stable. Even slight variation in equal variances, p-values don't go too wacky on us, but any violation of independence, we get p-values that are very unstable. So 3 assumptions need to be met, okay? So here's kind of what Tukey did, okay? Now again, let's focus on this right here. What he did was kind of a stroke of genius in that he compared group means. I can't handle that. Let me rewrite that. He compared group means by examining the ratio of variances. First time I heard of ANOVA many moons ago, I thought it was some sort of technique to analyze variance. It's actually not. Well, actually it is. We analyze variances to look at the comparison of group means. And essentially what he did was this. He established what was called a variance between and a variance within. So if we have distributions and we come in each of these and draw a sample, we don't know where the sample is going to be in there. Okay, so population 1, population 2, population 3, population 4. We draw a sample from 1, sample from 2, sample from 3, sample from 4. Now, notice that the variation within the distributions, as I've drawn them, are all about the same, right? I didn't come in here and draw some distribution that looked like this. Or I didn't come in here and draw some distribution that looked like this. All of the distributions that I drew here had equal variance. Why? That's an assumption. That's something we start out with in ANOVA. We have equal variance, which says the kind of the inner shape of the distributions are all going to be the same. So Tukey came in and called that the within variation, the variation within the distribution. Then he thought, well, let's look at the variation between the distributions. And let's look at the ratio of this. So let's look at the ratio of the variance between divided by the variance within. Well, he controls this right here, the variance within the distribution, by saying that we're really not going to allow these variations, these within variations to fluctuate because we're making them equal. The assumption again is equal variances. So this value right here is stable. Now, when is this value going to get larger? When's the variance between the distributions going to get larger? Well, when there's a bigger difference between the distributions. Well, what's that going to indicate? Different population means. So at the end of the day, he builds a test statistic, which he conveniently called the Fstatistic. Again, his name is Fisher. If I ever come up with a statistic, I'll probably call it the D statistic for Doug or something. Who knows? So the Fstatistic actually comes in and analyzes the ratio of the variation between the distributions divided by the variation within the distributions. Well, he starts to give this some big old fancy names. And what he called the numerator is the mean square of the factor term. And some, let me just put this up here, some textbooks you'll see this called the group term. Now guys, this is really getting into some important stuff because we're going to look at what we call regression for, ANOVA for regression. Right now we're doing ANOVA for group means. So this is going to be a technique that's going to stay with us throughout the entire semester, throughout the entire summer. He calls the bottom the mean square error term. Now each of these is divided into what we call the sum of squares for the factor divided by the degrees of freedom for the factor, all divided by the sum of squares for the error divided by the degrees of freedom for the error. So again, this is a ratio of the variances between and within. This part up here is called the mean square. So the sum of squares divided by the degrees of freedom for the factor is called the mean square factor. And in the denominator, the sum of squares for the error divided by its degrees of freedom are equal to the mean square error term. Now, we need some notation before we get too crazy here. First of all, and this is my notation, I tend to do it different than a lot of textbooks. First of all, we're going to let K equal the number of groups. So K is the number of group means that we're going to compare. N sub I is going to be the sample size of the ith group. X bar sub I is the sample mean of the ith group. And Sx sub I will be the sample standard deviation of the ith group. More notation. N will be equal to what I call the grand sample size. So N is just N1 plus N2 plus N sub K. And X bar, cap X bar, is just the grand mean. So that would be the the mean of all the groups when combined. So our test statistic is the F statistic. And the F statistic follows what we call the F distribution with degrees of freedom k minus 1, comma, n minus k. So the F distribution is a function of 2 degrees of freedom. So we enter in 2 values. Now, the F distribution in general, the t distribution and the normal distribution are bell-shaped and symmetric. The F distribution is a positively skewed distribution. So when we calculate our F statistic, let's see, let's get this where you guys can read it. Let's put it up here. So when we have our F statistic, the value to the right of our F statistic is our p-value. So there's no need to consider a two-tail p-value in an F statistic. The p-value is just the area to the right of our F statistic. Okay? Well, gang, the formula for the F statistic. Let's see if I can write this. So the sum of squares for the factor will be the sum from I equals 1 to k of, shoot, I forgot, n sub I times x bar sub I minus the grand mean quantity squared over its degrees of freedom, which is k minus 1. So all of this stuff up here, this is called the sum of squares for the factor. This is called the degrees of freedom for the factor. And all of this is called the mean square for the factor. In the denominator, we have the sum from I equal 1 to k of n sub I minus 1 times the variance of each group divided by n minus k. So gang, this part right here is known as the sum of squares for the error. This is the degrees of freedom for the error. And the whole thing is called the mean square for the error. Notice that your degrees of freedom for the group term, or the factor term, and the degrees of freedom for the error term are what we use to define the F distribution, which is ultimately used to calculate our p-values. Okay? Now let's run one of these. What I want to do now, so let's just run an example. I'm going to leave a lot of the calculations on this to you, but I want to show you, how to do some things. So let's go over to R. Maybe. This is fun. Oh, well, I'll tell you what, I have put up I don't know how many videos, and I've never seen my computer run this poorly. Okay, now let's run one of these. So I'm going to just use the same data set that we've been using. So I'm just going to call it data and read.csv. And I think I called this READ. So I need to attach it. And everybody always wants to see the data. I really could care less, but I'll do that because it seems like all my students always want to do that. Now, what I'd like to do here, the goal, I want to run an ANOVA showing the calculations for read over school district. Now, if you examine school district, you can see that there are 1, 2, 3, 4 groups. So for school district, K is equal to 4. Okay? Fair enough? Now, I'm going to need to create some things here. And so, one of the first things I'd want to do in running one of these is, well, actually, let me back up a little bit here. Okay, right now, R sees school district as quantitative. It sees school district as 1 unit. It sees school district 3 as 3 units, 1, 2, 3, just like 3 jelly beans or 3 golf balls. It doesn't see it as 3 distinct different school districts. So we have to tell R that we want school district to be categorical. Now, the way we do that, we'll rename it, and I'm just going to rename it as school. And we have to rename it as a factor. So once we do that, no bells and whistles. But I have to do that. Otherwise, you think about ANOVA. What's the criterion for ANOVA? We've got a quantitative variable, read, that we want to test the quality of the population means over K groups. If R isn't seeing school district as groups but quantities, it's not going to perform the calculations correctly. So I have to make the change in school accordingly. Okay. Now, first thing I'd want to do is think about what I need. Well, first thing I need is the total mean for read. So guys, I don't know about you, but I'm going to go along and write this stuff down over on the blackboard. So the overall mean, the grand mean for read is going to be 59.6. Now, I think it's going to be beneficial if I get out of this and go back over and show you what I'm doing. I've got a grand mean of 59.6. I'm going to need the sample mean for the first group, second group, third group, fourth group, as well as the standard deviation in sample size. So I'm going to do that. And I should know from the previous video on two-sample t-test that I can use t-apply, read, school, and function equals mean. Alright, so my means across group means are going to be 68.43. Uh, 55.71, 54.22, and 61.57. So just give you an illustration of what I'm doing here, just the obvious. Okay, next thing I want to do is go into R and get the standard deviations. So I'm going to run the same thing. And I want to make a note of those. So 16.74. 17.42, 30.81, uh-oh, why did I say uh-oh, and 24.95. Remember guys, we need equal variances. So I'll give you a couple things to think about there in just a second. Alright gang, let's, I don't know what the sample sizes are. I'm glad I checked. I thought they were equal sample sizes, but they're not. So 7797. And just so there's no misunderstanding, 7 plus 7 plus, what do we have, 30 is our grand sample size. Alright boys and girls, let's get out of R. Well, not get out of it. Huh. Well, shoot. Alright, so here's what we have going on. We have our cap N is 30. The grand mean for all 30 observations for read is 59.6. sample sizes. So these are the n sub i's. These are this is the I, and this would be our ith group. Okay? Now, calculations, I guess we're ready to carry those out in just a second. Now, let's go back and let's, before we start pushing a bunch of buttons that don't need to be pushed just yet. First of all, the assumptions are independence. And the best way to ensure independence is a random sample. So that's actually something that we take care of in the design of our study. So we're assuming that we have randomness here. The next thing we want is equal variances. And I'll show you a couple ways that we can take a look at that. And the next thing we want is normality. So one way that we can check both of these is to do side-by-side box plots. So if I go back over to R and come down and do box plot and do read over school, this is what I get. Now, for the most part, I'm not looking from the upper level to the lower level. What I'm looking primarily is I'm looking at the IQRs, the difference between Q3 and Q1. And there's a difference here clearly in the third group with the first and second group. So I'll be honest with you, I have a slight concern with equal variances. It looks like my distributions are pretty symmetric. There are no outliers. So the normality assumption I'm not as concerned with. For example, what would give me concern for a box plot in normality? Guys, if I were looking at a box plot and it looked like this, then I would be concerned with normality. Perfectly symmetric distribution. We'll have a box plot that looks like this. I don't see this as evidence in any of the side-by-side box plots. Now, there's another kind of a rule of thumb to test the equal variances that's actually pretty solid. If you'll take the low standard deviation, multiply that by 2, as long as the maximum standard deviation is in this interval, then we're pretty safe with the equal variance assumption. Now, if we go back to our lowest standard deviation is 16.74, right here. So if we look at the interval from 16.74 to 2 times 16.74, which is 33.48, we need our largest standard deviation, which is 30.81, to be contained in that interval to assume equal variances. And you can see that it is. So it's an informal way of testing, but it's one that's actually kind of agreed upon for taking a look at equal variances. So I'm going to go ahead and assume we have normality. I'm going to assume we have equal variances, and there's certainly not reason to suspect we don't. And I'm going to assume that the data was collected in a random fashion. So all three assumptions are satisfied. Now the next thing, I'm going to begin calculations. And first thing I'm going to do is my degrees of freedom. So the degrees of freedom for the factor term is again k minus 1. So our degrees of freedom for factor is 3. And the degrees of freedom for the error term are 26. So guys, our F statistic will follow the F distribution of degrees of freedom 3, 26. And I can just tell you that that thing is going to look something like that. So when we can find this value, the area to the right is going to be our p-value, which will ultimately make our decision. All right, gang, let's go for it. Let's officially carry out the test. So we're going to test mu1 equal mu2 equal mu3 equal mu4 against at least one pair of means is different. As I don't see any reason not to test at 0.05. You know, you might want to examine the consequences of a type 1 and type 2 error. I'm not going to do that. I'm going to assume 0.05 is suitable. All right, the next thing we're going to need to do is we're going to need to get the sum of squares for the factor. Now remember, this is the sum from I equal 1 to k of n sub I times x bar sub I minus the grand mean quantity squared. Now, gang, I'm going to get some of the calculations started for you. I'm not going to do them all. I'm going to leave that up to you. So I'll tell you what I'm going to do. I'm going to hold on just a second. I'm going to grab my phone. All right, I'm back. I'm going to grab my phone and I'm not going to call anybody. I'm going to grab my phone and take a picture, actually. I want to go back to this screen right here. And take a picture of those values. All right, because I don't want to go back and forth on things. Okay, so we're trying to come up with this sum of squares for the factor, and it's going to be calculated as the sample size times the sample mean minus the grand mean, which, daggone it, I forgot. Shoot. 59.6. All right, let me write that down because I'll guarantee you I'll forget it. All right, 59.6 quantity squared plus 7. 55 point. And by the way, we'll run this on R. I'll show you how to run this. Let's see, 61.50. Shoot, Doug, stop it. 7. And remember, this would be 9 times. So 7 times 61.57 minus 59.6 quantity squared. And whatever this value turns out to be, that's going to be your sum of squares for the factor term. Now, the sum of squares for the error is going to be found by taking the sum from I equal 1 to k, which is 4. And we're going to have n sub I minus 1 times the variance for each group. Alright, gang, so we're going to have 6 times 16.74 squared plus 6 times 17.42 squared plus 8 times 30.81 squared plus 6 times 24.95 squared. So again, whatever that value is there, that will be your sum of squares for your error term. Okay? Now, I've already gone ahead and worked this, sort of. No, I haven't. Yes, I have. If I can find it. Yeah, here we go. Now, it turns out that the values that I got when I worked this out, actually, to be honest with you, I just worked it out on the calculator, so it's not like I can do this stuff in my head. We know that the degrees of freedom for the factor is going to be 3, and we talked about that, and the degrees of freedom for the now they're going to be 26. I did say that, right? Yeah. For some reason I thought I said 28. I'm like, whoa, that's not right. The sum of squares for the factor, at least what I got with my calculator, was 938.79. And the sum of squares for the error, I got 14,832.41. Now, breaking that down into the mean square for each, the mean square for the factor, I got 312.93. And the mean square for the error, I got 570.48, which ultimately gives me an Fstatistic of 0.549. Okay, and yeah, I went out on all the calculations. Like 4 places. I think this is probably going to be pretty close. So in calculating the p-value, what we need to do is we need to, in the F distribution, degrees of freedom 3, 26, we need to find the area to the right of, I did say 0.549, right? Of 0.549. Okay. All right. So let me show you how to do that. On R. Now, if we wanted area for the t distribution, we used PT. Well, if we want the area to the right of the F distribution, we use PF. But guys, think about it. We need the area to the right, so we're going to have to subtracted from 1. And we went to the right of 0.549. And we have degrees of freedom 3, 26. Oh, that's just lovely. Oh, okay. There we go. So, guys, make a note to self. Don't use a capital F. Use a small f. So, guys, the area to the right of 0.549 is going to be 0.65. Okay, so what's the significance of this 0.65? That's our p-value. Which is clearly bigger than alpha, 0.05. So we fail to reject. Now again, you let someone with limited statistics background get a hold of this data, and what are they going to do? They're going to look at the descriptive statistics, and if I can ever find those, then they're going to say, well, yes, clearly, Group 1 had a higher reading score. Yeehaw for district number 1. They're awesome. They're almost 14 points higher than district number 3. No, they're not. Okay? These 7 students from district number 1 are about 14 units higher than these 9 students from district 3. When we generalize to the entire population of district 1, district 2, district 3, and district 4, we have to use inference procedures. And the inference procedures tell us that these mean differences aren't far enough away to conclude the population means are different. Guys, that is a very important part, especially those of you that are going through our full program, the master's program, and you're going to be doing the research sequence. We're focusing our research, at least the first couple of cohorts, on methods that will improve instruction. You start saying wacky stuff like this, you and I are going to have problems, okay? We can't do that. It's not the way it works. Okay, the final step, so we're failing to reject. So failing to reject says the evidence from our test says that there's no difference in the population mean read scores across the school district. Now, what if there were? So I'm going to file this under what if. What if we did reject the null? How would we determine? Again, if we reject the null, we kind of buy into the alternative hypothesis, which says at least one pair of means, could be 1 and 3, could be 1 and 4, could be 2 and 3. How would we determine? If at least one pair of means was different, how are we going to determine which pair of means is statistically significant? Answer? We do what's called a post hoc analysis. And a post hoc analysis actually comes in and makes multiple comparisons to focus on the statistical significance of the group means, taken 2 at a time. But it does so where it doesn't violate or inflate the type 1 error rate that we talked about earlier. It's going to allow us to go in and compare group 1 and group 2, group 1 and group 3, group 1 and group 4, 2 and 3, 2 and 4, 3 and 4, but not violate the family-wise type 1 error rate. Now, there are lots of different post hoc analysis. Bonferroni has a very, a commonly used one. Chaffee has one, and Tukey has 3 or 4, but the one that I prefer to use is called the Tukey HSD. So it's Tukey highly significant differences And I think probably, I don't know. I've seen all three of these work. Scheffé tends to be a lot more conservative, so it would be really appropriate to use in medical research. But anyway, in education research, I kind of prefer to use Tukey. All right, gang, I'm going to show you how this works on R, and we'll wrap up this video. This is kind of the cool part. Okay, so let's just go through the checks here. Okay, we have the quantitative variable, which is read, and we start out with school district, where you and I know that 1, 2, 3, and 4 are different locations. Those are different schools. R looks at that as 1 apple, 3 apples, 2 apples, 4 golf balls, 3 drivers, whatever it may be. You never tell I'm missing the golf course, right? Or wanting an apple or something, who knows? So we have to change that. And when we run into ANOVA, we have to come in and tell R that school district is actually supposed to be categorical. And you do that with the factor command. Okay? Now, the next thing we would do is I would just call it, my fit. And we would run an AOV, ANOVA, of read over school. Guys, don't get sloppy and run over school district. And I'll show you what would happen if you get this. If you did that, then you just you just get the wrong answers, which is not cool. So we run fit, and we get it, and we get this. Now, those numbers are going to look familiar, but I'm going to give you a lot better way of handling this in just a second. Okay? So once we get our ANOVA run, we can do what's called summary of our ANOVA fit. And guys, we end up getting what's called an ANOVA table. Now, let me go back and make sure the numbers that I gave you that I calculated, I know the p-value is fine, but let me go back. I got 570 and 312, so everything looks really, really good. In fact, we're off just very little. Okay. Now, let's see, where do I want to go from here? Let's talk about the let's see. Okay. I want to run the post hoc. Okay, let me point out one thing. This is not really a big deal in this ANOVA, but it's going to play a crucial part in the regression. Notice that you're given what's called a residual standard error. So you have a residual standard error. And guys, it turns out that the residual standard error will always be the square root of your mean square error term, which your mean square error term is 570.5. So guys, if you take the square root of 570.5, you're going to get 23.88, which is the residual standard error. Guys, the residual standard error in this ANOVA doesn't play an important role, but it's going to play an extremely important role once we get into regression and start reporting ANOVA for regression. So that's just kind of a side note. But what I really want you to look at is to perform a post hoc. Now, first of all, we perform post hoc analysis when we reject H sub O. Now, we didn't do that here, so the post hoc analysis, finding the pairs of means that are statistically significant, is a moot issue because we didn't reject the null. So we determined there's no statistically significant pairs of means, so we don't need to look for those. But what if we did? So let's just assume that we did reject the null and we needed to perform a post hoc analysis. So guys, the way you can do that on R is to perform a Tukey HSD. And Tukey, the T has to be capitalized and HSD has to be capitalized. We called our model fit way back here. So we need to type fit. And what it will do, it will come in and give us what it called the family-wise confidence intervals. So the first compares 2 and 1, which is going to be the same thing as comparing 1 and 2. The only thing will be different would be the lower limit and upper limit will be changed. So if we compared 1 and 2, our difference would be positive 12.71. Our lower bound would be negative 22.30. And our upper bound would be positive 47.74. Nevertheless, our p-value is not less than 0.05 in any of these cases. And in every single confidence interval, notice that we have what's called a negative positive. Remember that from a previous video? Negative positive contains 0, indicates not statistically significant. So at the end of the day, we're coming in and performing multiple two-sample t-tests, but we're doing it in a manner that was created by Tukey that protects the inflation of the family-wise type 1 error rate. So guys, we're finding no statistically significant pairs of means, which we should have because we had a test that was not statistically significant. Well, gang, I hope this is making sense. We're getting ready to get into some pretty good stuff. I'm probably going to put up a short video on dependent sample means, just because I want you to kind of have that on your radar. And but pretty soon we're going to get into the good stuff, and that's actually what I look forward to. I always question whether or not I should cover this stuff in a graduate level class because it's really primarily what I expect my undergraduate students to be able to do. But you know, as I think about you guys, there's you come to me with lots of different backgrounds. Some people have been out of school for a year, some 2, some 5, some 30. So I'd rather not build a house on sand and make sure that I adequately cover things like an ANOVA. And you know what? I'll guarantee you somewhere of our 24 students and well, actually of our 32 students total, somewhere I bet you there's some students that's never seen ANOVA. So hey, this is for you. Well, actually it's for everybody. So gang, I'm rambling. I'm just going on and on. Actually, I'm happy because it's Friday afternoon. I'm done putting up my videos and now I get to go mow grass. So yeehaw. Guys, have a good one. This will be the last video that I'll put up before Memorial Day. So have a safe one. Take care.